Assalamualaikum warahmatullahi wabarakatuh. Today, our group will be presenting development of gas chromatography method for the analysis of Copaiba oil. Our group members are Muhammad Aiman Hamizan bin Muhammad Nordin, Muhammad Amin Syahir bin Muhammad Zulkifli, Muhammad Qaid Irfan bin Kamaruzzaman, and Muhammad Farizz Iskandar bin Muhammad Yazid. Introduction. The principle of separation in gas chromatography analysis. The sample is therefore partitioned between the gas and a small layer of a non-volatile liquid maintained on a solid support, resulting in separation. A sample containing the solutes is injected into a heated block, where it is quickly vaporized and swept into the column inlet as a plug of vapor by the carrier gas system. The stationary phase absorbs the solutes, which are then dissolved by a fresh carrier gas. As the sample moves towards the outlet, the process is repeated in each plate. Each solute will go through the column at its own pace. Depending on the partition coefficient and band spreading, their bands will disperse into discrete zones. The solutes are eluted one by one in increasing order of the partition ratio KD and enter detector attached to the column's exit end. As a plot of time versus composition of the carrier gas stream, they record a succession of signals resulting from concentration changes and rates of elution on the recorder. Quantitative data can be obtained by measuring the appearance time, height, width, and area of these peaks. Copaiba essential oil is made from crude extracts of the Copaifera reticulata tree in Brazil. It has a high concentration of the naturally occurring ingredient beta-caryophyllene, making it ideal for use in skincare products. By using gas chromatography, a rapid, simple, precise and cost-effective method for quantifying the main compounds of Copaiba resins and essential oil has been developed and validated. This is the schematic diagram of gas chromatography. It will start at the carrier gas, move on to the flow control and then into the injector port. At the injector port, the sample is injected and vaporized onto the head of the chromatographic column, where inside the column, the separation is based on the difference in migration rates among the sample of components. Next, into the detector, which is as each component emerges from the column, it will be detected into the recorder. The importance of the main part of gas chromatography. The heart of the gas chromatography is the column, which is made of metal bent in U-shape or coiled into an open spiral shape. Several sizes of columns are used depending upon the requirement. In the gas chromatography system, a sample is vaporized and injected into the head of separation column packed with a finely divided solid or coated with a film of liquid. When a sample traverses the column by the flow of an inert gas employed as the mobile phase, its components are separated owing to differences in their interactions with the stationary phase. Upon elution from the column, the separated compounds pass over a detector that generates a signal corresponding to the concentration of the compound. The species present can be qualitatively identified based on the delay in the sample passing through the column.
Next is for the methodology part. First, the extraction of the essential oil. Copaiba essential oil was obtained by hydrodistillation from the Copaiba resin using Clevenger apparatus to separate the colorless volatile fraction of the viscose residue. The yield of this extraction was calculated as the ratio between the volatile oil obtained and the resin material used initially for extraction. Next, Copaiba resin derivatization. The procedure was used to prepare detectable low vapor pressure compound and thermally stable derivatives. Determination of beta-caryophyllene, alpha-humulene, and caryophyllene oxide in Copaiba essential oil and resin by GCFID. Stock solutions 10 mg ml-1 of Copaiba essential oil and resin were prepared in triplicate with ethyl acetate. These solutions were diluted if necessary to obtain solutions with concentrations that fall within the calibration range. Samples were injected in GCFID in the same conditions as the validation studies. Quantitation of beta-caryophyllene, alpha-humulene, and caryophyllene oxide was performed based on the standard calibration curves of the individual compound. On the right side, there is a table for parameter and condition for GCMS.
Now is the results part. Copaiba essential oil was obtained by hydrodistillation from the Copaiba resin using Clevenger apparatus to separate the colorless volatile fraction of the viscous residue. This is the flowchart of the quantitative and qualitative aspects for the Copaiba oil characterization. To improve resolution and reduce analysis time, the gas chromatography flame ionization detector method for Copaiba resin and essential oils transposed and optimized. The retention times were only slightly changed because of this adjustment, but neither the peak elution order nor the relative peak area of the compounds were changed. As the results, a validation method was carried out utilizing beta-caryophyllene, alpha-humulene, and caryophyllene oxide as reference substance to quantify the compounds. These good terpenes were chosen since they were found in the every Copaiba oil sample previously examined. For these chemicals, the approach yielded good resolution indicating high specificity and selectivity. This approach was particular to the standards and did not interfere with the retention times peaks. Mass fragmentation in gas chromatography mass spectrometry confirmed the purity of the peaks. Gas chromatography flame ionization detector test revealed the retention duration of 13.15, 14.87 and 21.52 minutes. Beta-caryophyllene, alpha-humulene and caryophyllene oxide respectively. The presence of an impurity eluted after beta-caryophyllene was discovered, and a chromatogram of beta-caryophyllene peaked at 14.9 minutes. According to the mass fragmentation profile identified in gas chromatography mass spectrometry, this little peak corresponds to alpha-humulene.
So, lastly, let us jump to the conclusion. In conclusion, GCMS analysis was used to identify compounds found in Copaiba resin and essential oil to enable for the tentative identification of the terpene components from Copaiba resin. A derivation was performed. The elution profile of Copaiba resin and essential oil components were consistent between the GCMS and GCFID methods, allowing the method to be transposed from GCMS to GCFID. It was found to be suitable for absolute quantification of beta-caryophyllene, A-humulene, and caryophyllene oxide in Copaiba oil samples, with sensitivity superior to previously proposed approaches. The approach may be used to quantify B-caryophyllene, A-humulene, and caryophyllene oxide in Copaiba resin and essential oil samples as demonstrated in these studies. Working group on method of analysis on both a qualitative and quantitative analytical basis. The methods described in this study might be offered for quality control examination of previous products made from Copaiba oil extracts. Thank you.
Lastly, for the reference, these are the articles that we gained for this assignment. That's all from us. Thank you.